Welcome again, Betas, to a new lesson. So, as you can see, we are still in lesson 1.1.2, and this is because we haven't made justice for the Kronecker delta and the Levi-Civita symbol. And what I mean by that is that we have only seen their definitions, but we haven't seen how they are used, so they are useless. Well, this is kind of redundant, but you get the idea. We need to see how they are used. So we are going to split this into two videos, because if I were to explain everything in one video, it will get very long, and I want to stick with the dynamic of the videos being like 10-15 minutes. So we're going to begin with the Kronecker delta, and we are going to relate the Kronecker delta with a dot product. So in the first lesson, we saw an example of a dot product, which was this equation. The rate of change of work or energy is just the dot product of F with V, and we could write this with the Einstein summation convention as this. So it will seem that in order to take a dot product, we don't need the Kronecker delta, because we just make the two indices of the vector equal, and that's it. That's the dot product. However, this is not true, because we have to remember that we are doing all this analysis in a Cartesian coordinate system, although we haven't stated that explicitly. But for example, if you have a vector in spherical coordinates where, I don't know, let's say we have AR, A theta, A phi, okay, we have the three components in spherical coordinates of a vector, and we have also another vector in the same form. The dot product of the two vectors isn't just AR, BR plus A theta, B theta plus A phi, B phi. You get the idea, right? So for example, in spherical systems, in a spherical system of coordinates, this isn't just true. Well, this is true, but it isn't true that the dot product of the two vectors is this. This is not true. So we have to remember and take into account that we are only working in Cartesian coordinates. We'll see later that we need something which is called a metric to take a dot product between two vectors. So before introducing the metric, which is a little more advanced concept, we are going to introduce this other concept, which is that we need an object, in this case the Kronecker delta. We need an object to take dot products between vectors. So in this case, in Euclidean coordinates, or in Cartesian coordinates, in an Euclidean flat space, this object, the metric, will be just the Kronecker delta. But we'll see that in later lessons. So we are going to take as an example two vectors. We are going to represent them in index notation as this. And we want to compute their dot product. So we are going to take as a definition of the dot product the two vectors multiplied together independently. Okay, so it's important that they have different indices. And now what we are going to do is to multiply this object by the delta ij. So the delta is going to do something which is called a contraction, which is going to make the two indices to be the same. But we're going to see why that's true. So we can remember by the Einstein summation convention that we can expand this out as a double sum. And for the sake of this course, well, for this lesson, I'm going to write this time explicitly every term of the sum. This is the first and last time that I'm going to do this, but it's important that at first, when we are dealing with the Einstein notation convention for first time, it's difficult to see that, for example, here we have a double sum. So it's clearly to state from the beginning that we are summing things that apparently aren't summing. So if we compute the sum, we are going to make the I index to be 1 and we are going to vary the j index. So now the j index is 2, I is still 1, now the j index is 3, and now we are going to do the same but for I equal 2. So as I say, it's important when you start dealing with index notation to write everything explicitly a few times so that you get used to what's happening when you are writing formulas. So this is something important to do when you are first learning index notation. Okay, we're almost there. Okay, so if we remember the Kronecker delta, when we have a component with two different indices, it was equal to 0, as you can see in these two examples. And when the indices were equal, it was 1. Okay, it's just the definition which is written here. So we can start to discard some terms. For example, this is going to be 0, so this term vanishes. The same for this one, this is 0. The same for this one, it's 0. And for this one, also for this one, and for this one. Now here we have that this is equal to 1, so this just disappears, but we are maintaining this. This is also equal to 1, and this is also equal to 1. So what we are left in the end is just a1b1 plus a2b2 plus a3b3. So the Kronecker delta just made this transformation, if we can call it by that. Okay. Well, we already know that here this thing is equal to this other thing. Remember that this is by Einstein summation convention, this thing. And you can also see that we could have written any other index. So I have written I, but I could have written also, I don't know, let's say j. Or I could also have written k. Okay? So this is a very important concept about dummy indices. If you remember what we said in lesson 1.1.1, I think it was that lesson, yeah. So these are dummy indices which are summing together. It's said that they are contracted. So contract indices are like, well, are that thing, dummy indices, are the same thing when you are summing something. For example, I don't know, if you have a Taylor series of a function and you have x to the n over n factorial, n from 0 to infinite, it's the same thing as writing just m equal to 0 to infinity of x to the m of n factorial. So you can change the tag that you have for the sum and nothing changes. So it's the same concept here. It's the same summing for I, for j, for k. Okay, it's just the very same thing to do this than to do this other thing. Okay, the dummy index is just a tag that you put to the vector, and when it's contracted to other index so that both indices are dummy indices, you can change the tag because it doesn't affect, because it's just a sum. However, if it was a free index, you couldn't do that unless you do it also to all the free indices. But we'll see that in later lessons, some examples. So what's important is that we can see that some properties, well, a property of the Kronecker delta is that it makes contractions. So what does it mean? Let's say that I have now an object. Okay, well, let's say we have also another two vectors. I'm going to write them as this, and we contract them together with the Kronecker delta. We'll now see in a moment why it's called a contraction. So you can think of the Kronecker delta as an object which takes one index of the two it has, let's say the m, and when you see another m, because this m is summing with another m, it's contract with another. So what it does is that it kills the m's and now it substitutes in the k. So this will be ck dk. Okay? Well, we could also have said that the Kronecker delta, it kills the k, and now it substitutes in here the m. So we will left with instead with cm the m. But this is the same as we have seen here. It doesn't matter the tag we put to the dummy index. So the key feature about the Kronecker delta is that it collapses indices. Okay, so if the two indices of the Kronecker delta, it collapses one of the two into another. So let's say we have another object, which in this case it has, let's say, two indices, and we have here another object but just with one index, and we multiply by the Kronecker delta of jk. So what do you think that this would result in? Okay, so let's say, for example, that we kill the k and now we substitute in the j in here. So it would be tij aj. So we see that the Kronecker delta contracts the j and the k, these indices, it contracts them together and it makes them both dummy indices which are summing together. So this is the key feature about the Kronecker delta. We can also see this as when we have the double sum, we can write here let's see. So the Kronecker delta, every term of the sum is going to be 0 unless I equals to j. So what it's going to do to the double sum, it's going to kill one sum, and when in this sum we have j, because j is going to run from 1 to 3, and the index I is going to be one of those values. So unless j equals to I, it's going to be 0 every term. So the Kronecker delta in both sums, it kills one of the sum, and the index of that sum j, it put in the I. So this is going to kill one sum, and we are left with just only one sum, let's say for example I. And now where we have the j index, we write the I index, and it's just the same as we have seen previously. So you can think of the Kronecker delta as this object which contracts some indices, and also as the object which kills one sum and substitutes back the index of the sum that we killed to the other that survived. So in the next lesson we are going to relate the Levi-Civita symbol to the cross product. And one more feature that I wanted to say before finishing this lesson is that we can do a matrix representation. So let's say that we are going to grab this and we can reorder this into this other thing. And now we can think of this, if we make like a matrix analogy, this will be something like this. So I already mentioned in the lesson 1.1.1 that you could grab all the deltas, all the possible deltas, all the components, you can arrange them in this way. And if you form a matrix and you compute the components, this is just the identity matrix. So if we transform this into a matrix form, it will be something of this kind. And if you perform the operation, it's just going to be, well, what we found previously. So this is the reason why it doesn't matter to write AI BI as a dot product, because here we have the identity matrix, and while the identity matrix times a column vector is just the column vector, so this is as if this didn't exist. However, this matrix is identity matrix because we are in flat Euclidean space and we are using Cartesian coordinates. So it's very important to take into account that we need an object to do the scalar, to do the dot product. We can't just simply write this. One last thing that I wanted to mention, and the video is getting longer than I expected, is that you can interchange the indices of the Kronecker delta and everything stays the same. So this happens because if we have delta 1, 2, it's going to be 0 as well as delta 2, 1. The same for 2, 3, 3, 2, and when you have the same indices, I mean, you interchange them and nothing changes. So this is a property that we'll see also in later lessons, and this is called a symmetry. Well, this is called symmetric tensor. So we'll see what are tensors, okay? But the key idea is that when we have something symmetric, it means that we can interchange both indices and nothing happens. And you can see where this word of symmetric comes, which is that the matrix representation for the Kronecker delta is a symmetric matrix. So this is like a very deep analogy, and it's very interesting. So we'll see in later videos some property of symmetric and also anti-symmetric tensors, but we'll leave it for other lessons. So the next lesson is going to be about the Levi-Civita symbol, and we are going to relate the Levi-Civita symbol with the cross product. And spoiler alert, the Levi-Civita symbol is an anti-symmetric tensor. Well, it's an anti-symmetric symbol. No, we are not going to see tensors yet, okay? So see you next lesson.